Hello, everyone. I'm Ionel, and I'm a postdoc in the RISE lab working with Jan Stoika. In the next 10-15 minutes, I'll give you a high-level view of the projects you're going to hear about and the tutorials you're going to complete today at this RISECamp. Our two-day workshop is focused on two main themes. In the first day, we'll cover some of the systems we developed for supporting emerging AI applications. In the second day, we'll switch focus to systems for data analytics and security. Today, you're going to learn about RAY, which is a distributed framework for emerging AI applications. After a short break, you're going to hear about RLlib, a library for building and running distributed reinforcement learning algorithms. Next, we'll have a lunch break followed by two tutorials. The first one will be about Tune, which is a framework for distributed hyperparameter search. The second tutorial will be about Clipper, which is a low-latency prediction serving system. And finally, we'll have a last break followed by a session in which you're going to learn about Flor, which is a system for managing the workflow development phase of the machine learning lifecycle. Ray is a system that enables users to run parallel and distributed Python code. It was built with three design goals in mind. First, ease of use. Users should be able to parallelize their existing code with a minimal number of code changes. Second, flexibility. Many AI applications combine different types of computations, such as running neural networks, planning, and executing simulations. It is challenging to combine these different types of computations because some of them are stateful and some of them are stateless. Moreover, these computations, they have different requirements in terms of resource. Some require more GPUs, some more CPUs. And they also have different runtimes. Some are very short running, whereas others are long-running tasks. Ray strives to support flexibly all these types of computations by unifying the actor and the task parallel abstractions on top of a dynamic task execution engine. The third design goal is performance. One characteristic of the applications we target is that they can generate hundreds of thousands of short-running tasks per second. Ray was designed to schedule millions of short-running tasks with millisecond-level scheduling latency. And Ray is different from other solutions because it can offer both high task scheduling throughput while maintaining low scheduling latency. In the course of the Ray tutorial, you're going to familiarize yourself with the Ray API. What you'll learn in this tutorial will serve as a base for several other tutorials, including an exciting integration tutorial that combines 4 of our systems. In the Ray tutorial, you're going to learn how to run tasks in parallel using Ray, create dependencies between tasks, encapsulate mutable state, such as stateful simulators, in actors, learn how to deal with struggler tasks that take longer to complete than others, use Rays with GPUs, and you will even learn how to implement a distributed tree reduce in Ray. In case you don't know, Ray is already open source, and we've recently released version 0.5.3. This version brings many new features, such as support for Java. Moreover, the release includes a substantially refactored backend. In this backend, we no longer have a global scheduler, and we don't include the global store and the critical scheduling path. Moreover, we'll also improve the data transfer between tasks and actors. In the future, we plan to provide a streaming solution on top of Ray to address the fault tolerance of the global store through chain replication and to improve fault tolerance, actor fault tolerance. Next, we'll have a tutorial on RLlib, which is an open source library for running scalable reinforcement learning algorithms. RLlib offers both a collection of reference reinforcement learning algorithms and also scalable primitives for implementing your own algorithms. As you can see in the figure, RLlib extensively uses Ray and interacts with single or multiple agent environments. In the course of the RLlib tutorial, you will learn how to model problems as RL environments. In particular, you'll interface with the OpenAI gym environment that simulates the physics of balancing a pole on a cart. You're going to use RLlib for distributed training simulation. Using RLlib, you'll be repeatedly rolling out a large number of policies in parallel, find the policy that maximizes the objective, and update the policy weights. Finally, you're going to use RLlib to set up a server that simultaneously serves and learns from a policy. Using this server, you'll be able to train and play against the Pong policy. RLlib is also open source and is included as part of the Ray release. In the last release, we've added support for multiple agents and recurring neural networks. In the future, we are going to continue building our multi-agent support and push out further performance improvements to enable users to push the boundaries of what reinforcement learning algorithms can do. Up to now, I've discussed about training models on many machines. However, in many cases, tuning the hyperparameters of these models is the most expensive part of the machine learning workflow. Tune is a framework built to conduct a scalable hyperparameter search. Tune users can choose among several scalable hyperparameter and model search algorithms, such as hyperband and population-based training. The framework currently supports several deep learning frameworks, such as PyTorch, TensorFlow, and Keras. And it can also scale to large clusters without you requiring to change your code. In the Tune tutorial, you're going to work with the MNIST dataset of handwritten digits. You're going to create and train a neural network model on this data set. The model will classify the handwritten digits. Next, you're going to integrate Tune into your workflow in order to find better hyperparameters so that the model trains faster and hopefully to a higher accuracy. Following, you're going to accelerate training further with an efficient scheduler that Tune provides. And finally, you're going to be able to play and try out the model you train yourself. Tune is also included in Ray. In the last release, we have collaborated and worked with Ant Financial to add new algorithms. Moreover, we've redesigned the system to make the execution framework agnostic. In the future, we plan to better integrate Ray to better integrate Tune with Ray, to offer a web UI, and as well to further improve performance and stability of the system. Clipper is the fourth system you'll learn about today. Clipper makes it possible to decouple applications from the machine learning models they use. In the figure at the top, we have a layer of typically interactive applications, such as Netflix movie recommendation, and at the bottom we have an increasing number of heterogeneous machine learning models and frameworks. Throughout this decoupling, Clipper allows these two layers to independently evolve and as well to be independently managed. Moreover, Clipper provides latency-aware prediction serving for the interactive applications that have latency SLO requirements. When applications submit queries, Clipper load balances them across a set of suitable models in an SLO-aware fashion. The Clipper tutorial is going to walk you through a set of basic exercises that are going to teach you how to interact with Clipper, how to deploy models, and how to send queries to the models. By the end of the tutorial, you will know how to deploy example applications that classify images and detect objects in images. More generally, in this tutorial, you develop an understanding of how Clipper works, and hopefully, as a result, you'll be able to use Clipper to power your own machine learning applications. In terms of status, we've recently released in June Clipper version 0.3. This version brought a series of improvements, such as Python 3 support, better metric monitoring infrastructure, and as well hierarchical scaling on Kubernetes. On the roadmap, we have many great features that are pushing the boundaries. Among them, I would like to mention that we are going to serve pipelines of models, and as well, we're going to provide auto-scaling. Finally, in the last tutorial, you'll learn about a system that we are building for managing the workflow development phase of the machine learning lifecycle. Data scientists and machine learning practitioners like to try out ideas as quickly as possible. However, this creative process of trying out ideas and experimentation can be at odds with the expectation of rigorously tracking experiments, setups, and parameters. As a result, it is easy for data scientists to neglect the necessary steps that are required to ensure that their experiments are reproducible. Flor is a system with a Python-based declarative DSL that addresses this issue. Flor provides a versioning system that enables users to preserve and track the evolution of experiments across different runs. It stores and manages all the data context generated through various activities that are part of the ML pipeline development and training process. Flor includes tools for annotating experiments, analyzing past experiments, and as well answering questions about experiments, results, and behavior. Lastly, Flor enables users to share experiments and as well to interpret the experiments other people have done. In the course of the Flor tutorial, you'll complete a series of exercises that illustrate how Flor improves the common interactive model training pattern. You will train a model to predict sentiment of English phrases, such that it can be positive or negative. You're going to try different setups, and you're going to see how Flor wraps the pipeline with just 3 lines of code. This will automatically bring you the benefits of versioning and annotation. Next, you're going to learn how you can interpret a Flor experiment someone else has shared with you, and how you can reuse some of someone else's artifacts in your own experiment. Lastly, you're going to annotate the experiment you've been developing in as much detail as possible, and as a result, you will not always have to rerun and retrain models, because you may be able to reuse models that you've previously trained. Flor is open source and comes with Apache version 2 license. It's currently pre-release, but hopefully we'll have a release in not too distant future. You can currently use the Flor version that is open source in both in an interactive way in Jupyter, and as well non-interactively when you're training your models. In the future or on the roadmap, we plan to add a global searchable context store in Flor, and as well to improve our support for interactive pipeline development. To conclude, I hope that you're going to enjoy the tutorials we prepared for you. Before I hand in to the next speaker, please make sure you either have a note with the network password, or if not, make sure you can connect to the network, because you're going to need the network access. Thank you very much.